Good morning, sir. Javis, sir. Live starting, sir.
Srinivas, sir.
Okay, sir.
Shall I start? May I start?
Start చేయండి, sir.
Respected DEO Khammam Suryapet and SCRT Physical Science Coordinator Anal Inquiry, sir, and respected co-RPs and my dear Khammam Suryapet Physical Science teachers and beloved children. Good afternoon. I am going to take light chapter Spherical Mirrors. I will give you some basic concepts on spherical mirrors. So let me share my audio and video. So children, this is meant for only children. That's why I'm using children word. We observe the images in different mirrors from top to bottom, and you remember how the images are formed in the mirrors. Are the images formed by bulged surface same as the images formed by a plane mirror? Definitely no. Why? Because notice the size of the image compared to the size of the object. You see here a side mirror of a two-wheeler. A big tree appears small in this side view mirror. Is this a plane mirror? Why is it showing small images? Just you think of children. How the images forms in the mirror. You see here, it is a mirror. What type of mirror you have to imagine? I will explain later. Observe the image. Why is it happened so? What is the reason behind it? You think over children. I will explain you. So what a drastic change. Up-down image turned to upright and the image is big in the mirror. You remember it. So think our children here, what happened? As the man moves closer to the mirror, the up-down image turns to upright, and suddenly at particular point it turns upright and the image becomes bigger than his face. Appears very big, in the image. So you remember what is drastic change. Do you have any question on this? Please share it. So this is a plane mirror, the mirror we use to see at home. You see, image of the elephant in the mirror, image of the cat, image of the fish. So what do you notice? As the size of the elephant, as the size of the fish, as the size of the monkey, image also same, but a small change will be there. You understood, I think. Only the right side appears as left side in the image. That, as you know, in 8th class standard, it is called lateral inversion. So I will move forward. You see, monkey is coming closer to the mirror. Image also coming closer. Monkey goes right. The image left side. How far from the mirror the monkey? The image also. Now let us take a plane mirror. Now try to press at the edges. So actually, the glass mirror doesn't bend like this. If you take acrylic mirror, it will change its shape from plane surface to curved surface. If you press at edges, it bulged out. The reflecting surface here, it bulged out. So its name already I think I will explain later. When we press at the edges, instead of plain surface, it turned into curved surface or bulged outwards. Now you see the change. These are called curved mirrors. You know that, children? The law of reflection, first law of reflection on plane surfaces. The light ray, when incident on a plane surface at a particular point, it bounces back into the medium in the same plane as a reflected ray. And if you put a normal, if you imagine a normal perpendicular at that point of incident, all these three lie in the same place. This thing you might have known at the 8th standard. Incident ray, reflected ray, and normal both lie in the same place. And here, particularly if you measure with protractor, the angle of incidence is equal to angle of reflection, children. You noting here. First law of reflection, does it apply only for plane mirrors? Is it applicable for even curved surfaces? Yes, definitely. Let us see. Angle of incidence as it comes from left side, the ray is bouncing back right side. That's the reflected ray. I is equal to 60, R is equal to 60. I is equal to 50, I is equal to 50. This law is true for all surfaces, whether it is a plane surface or a curved surface. Curved surface if angle of incidence is 30, angle of reflection will be 30. I is equal to R. If angle of incidence is 45, reflection will also 45. You see in the table. It is very easy to find a normal at any point on the plane surface, but for a curved surface, it is not straightforward. It is not so much easy to find the normal and angle of incident angle. Let us find the normal for a curved surface by an activity. You have this activity in your textbook also. What does it show? Here I used a foam sheet and broomsticks. You may use wire or a thermocol sheet or rubber sheet, anything which is flexible to bend inward or outward. Okay, children? Now you see the activity, virtual activity I performed in the video. You follow the video carefully. Little bit difficult to find. So this is foam sheet, children. Rectangular foam sheet, required material foam sheet and broomsticks. So in the video you observe the broomsticks are about 10 centimeters and foam sheet is about 5 to 10 centimeters. Let us fix the middle broomstick at the center of the length of the foam sheet, which is a level foam sheet, flat surface. If you consider the foam as a plane mirror, then each stick acts as a normal, perpendicular to the plane of the foam at that point of fixing. So they were fixed on the foam sheet like this. So now they are parallel to each other. They are straight. Left ends are fixed in the foam sheet. Right ends are free to move. Now you see the change. When I press at edges such that the foam sheet bends inwards, you see the right ends of the broomsticks. So the downward broomstick going up and up. The middle broomstick as it is straight. We will notice that all the sticks intersect. Here, if you consider them as light rays, they converge at a point. Still, they are representing the normal children. So, meeting at a point. That point, we later will come to know that. We press more, the curved surface increases, radius of increase decreases. So, the point of converging moves closer to the foam. That you have to observe. Whatever is your activity in the lab or at your school or at your home, you have to observe everything properly and you have to remember the drastic changes or any changes taking place while we are conducting activity. Okay, see, When I release the pressure at the ends, they're coming back to the normal parallel state. Now all the three, why I have taken three, it is easy to remember. If you may fix two more above or two more below. Now I am pressing at the edges that it bulges out, curving out. You see how the broomsticks are widened? So in the middle stick is straight as before in the first activity, but the upper stick and lower broomstick widened more. Now if you bend the foam outwards, then we will see that stick seems to be diverged as shown here. This. So imagine the light rays when they fall on a bulgy surface, they diverge like this. You have to imagine the light rays when they fall on, they converge like this. This gives us an idea of what is happening with the spherical mirrors. A concave
Jagdish sir,
mirror will be like the foam bent inwards or foam sheet bent outward. So initial broomsticks, how they are fixed on the foam sheet, we consider the light rays coming from a long source. They definitely from the long source will get a parallel rays. A convex mirror will be bent outward as shown here, bulged outwards. Convex mirror diverges the light rays and they fall on it, the parallel rays. Now, let us know about the basic concepts about the spherical mirror chip. What are the basic concepts we must know regarding spherical mirrors? That I will explain to you now through virtual video. Shall I move forward? See here, you see the spherical mirrors are taken from halosphere or sphere. One is coated outside, right here, from the left side spherical mirror, right side spherical mirror coated with red inside. These two are spherical mirrors only. Okay, remember and observe carefully. These are spherical mirrors. You see this simple, funny experiment. This is having a mirror in his hand. What happens? You see the fish coming in, and as the fish comes closer, so it appears big in mirror. This is funny. Yes, this is a concave mirror. So at particular distance of fish, when it comes closer, then only its image appears big in the size in concave mirror. Just you understand. When it is away from the mirror, no image is seen in the mirror. Concave mirror. Just for your fun sake. How far it has to come, I will explain.
Jagdish sir, Jagdish sir, జర వాయిస్ పెంచరా, వాయిస్ చాలా లో ఉంది అంటున్నారు పిల్లలు.
This is the problem of speaker, I think, sir.
ఓకే ఓకే సార్.
Here you see the experiment. A balloon filled with air is spherical, and I have placed a concave mirror over it. Imagine the spherical concave mirror is taken out of the sphere. Concave mirror is a part of sphere as shown here. Observe carefully. So this is also round, and of course its surface is not flat. It is curved surface. Observe carefully. This is a balloon. Imagine that balloon is a sphere of made up of transparent material. You see the line passing through the center of the sphere. Imagine a white spot is there. It is center of the sphere. So here I will have to explain you children about this spherical mirror. Concave mirror is taken out of the spherical halo spherical balloon. It is not a balloon. You have to imagine that is a halo transparent material. So the line passing through the center and the midpoint of the mirror, it is called pole of the mirror. And we notice a red spot at the triangle where I stopped the video. You can see the red point. What is the significance of this midpoint from the center of the concave mirror and the radius of total whole sphere, white spot. So this is exactly at the midpoint. I will explain you now. Concave mirror is a part of the sphere. Here the 2 points are here. Think about this. This is center of sphere, that also center of this concave mirror, and this red point. You see the ray passing through the center and the red spot and to the center of the concave mirror. The center of concave mirror is denoted by P, and the C is center of curvature of the sphere. That will be considered as the center of curvature of spherical mirror also. You see, children, the midpoint. What is midpoint? I will explain. There is a ray coming from far light sources. It will influence on the concave mirror, which is parallel to the principal axis. I have to explain what does this line is called. The line joining whole of the concave mirror and center of curvature is principal axis. This principal axis is not up to diameter. It will extend indefinitely. It is infinite. And I will explain you afterwards what about F and G. So the incident ray on concave mirror after reflection, where it passes, let us see. The one ray which is parallel to the principal axis incidents on the concave mirror and bounces back bounces back. This is the normal drawn from the center of the curvature to the point of incident of the light ray. Blue line is normal. You know that for a sphere, the radius will be the normal. So angle of incident is denoted by here with the white shaded part from the blue line to yellow line. Now you see, children, the incident ray bounces back, and that is passing through the red point, which is called the focal point. It is this angle of reflection from the concave mirror point of incident is shown by. Now you see, I am placing a concave mirror on a black sheet. You see how to find the focal length. So afterwards, this concave mirror, which you see now in the video, doesn't appear afterwards. To find its exact focal length, here we do like this. The rays coming parallel to the principal axis, after converging at a particular point, they diverge back. Where they are meeting, that point is called focal point. Right. Denoted by T. To find focal length. It's the mirror one side, and the rays falling onto it. When we move, they are converged at a point, and again they diverge. At that, where they are meeting at a particular point, that is called F. This is called focal. From this point to the mirror, the length between this F red spot previously in video, from that to the concave mirror is called focal length. Here I will show you. All the rays which are coming parallel to the principal axis, after the incidence on the concave mirror, they are passing through a particular point. Here it is shown by a red point. It is denoted by F, focal point. And here, the distance between the focal point and the pole of the mirror, concave mirror, is called focal length. The focal length is denoted by small letter F. Sorry for interruption. Video has been paused a little bit backward due to some technical issues. You see, here also finding focal length by using a concave mirror on a black sheet. Allow the light to fall on the concave mirror, and after converging, they again they are diverging from the point of converging to the concave mirror, we consider as focal length. Okay, this is way of finding focal length. That's why I did show again. Okay, this is way of finding focal length. Okay, children. Finding focal length of a concave mirror using a small activity, black sheet, flat surface, concave mirror. This way, unknown concave mirror is given to you. You can find the focal length by this small good activity which was not given in our text. Focus from the point of focus to the pole of the lens, concave mirror. You see there, the white spots here in this video, you have to observe carefully. I will go a little bit backwards about it while you observe this one. Sorry. You see here, children, the white small triangles are moving towards the concave mirror. After incident, they are bouncing back. First to one line and two lines, three lines parallel. They are not lines. Imagine they are light rays coming from far source. They are parallel to the principal axis. See, observe the video. After incidence on the concave mirror, they are passing through the focal point. Above two lines parallel and below two lines. The above two parallel rays after incidence of the concave mirror passing through it, coming downwards. The below two parallel rays after incidence on the concave mirror, they are bouncing back above the principal axis. Anyway, all are meeting at a particular point, significant point that is called focal point. And from that point to pole of the mirror is called focal length. See here, F to P, focal length. F to C is also same. F is midpoint of C and P. And from C to P is called radius of curvature. And F to P is called focal length. So you have to understand focal length of a concave mirror is half of the radius of curvature. R by 2 is equal to F, or R is equal to F, small 2F. Okay, you have to remember this. And if you have any doubts regarding this technology or the activity, you may consult your teacher and clarify your doubts. Thank you, one and all. Thank you. And you see, move. So this is a small activity. Here, you see, I have used a cardboard. Instead of this, you may use thermocol sheet or plastic sheet or plywood or any other sheet. So you see, I fixed the concave mirror on cardboard with glue or something else or tape or as you like. And the other side, exactly below the pole of the concave mirror, I have taken off sheet, and above that cardboard sheet, I placed a matchstick. Instead of matchstick, you may use burning candle or such. And these two are joined by a meter scale or measuring tape. See, observe this activity. You see. Then you have to observe carefully. The matchstick is not yet lighted. Afterwards, it will be lighted. See, when it is extended, its image can be seen in the mirror, and that image will fall on the same cardboard, which is far away from the concave mirror. And the size of the image which falls on the same cardboard changes as we move the burning matchstick flame. When it becomes closer, it's bigger. It is a virtual actual image, upright image. When it is taken away from the mirror, the image size decreases as it moves away from the mirror. And at a particular point, the size of the flame will be exactly equal. You know that when it is placed at C, center of curvature, the flame will be as size of the image. The image will be same size of the burning suppose. So this I did is my own idea given by my friend Aditya Kumar. He may use some other materials to do this experiment. The below scale was used. This is to measure the object distance and image distance. And instead of using meter scale, you may use a tape also. Or we are having in laboratory meter scale fixed stand also. That's very. But this is simple material used to find the focal length and object. Thank you, one and all. This is Jagdishwar, SSC Headmaster and Physical Science Teacher, Jagdishwar Mangal. Thank you. Siva sir, switch off the screen sharing. I will come back to the. Hello. Thank you each and everyone who have cooperated with me in presenting my lesson, and the future artists may present very well than me. I hope everyone gets success and reach the children properly. Thank you, one and all. Sir, thank you, sir. Siva sir.
సార్ అయిపోయిందా సార్?
Okay.
లైవ్ క్లోజ్ చేయమంటారా?
Okay, close it.
ఓకే సార్, థ్యాంక్ యూ సార్. ఓకే సార్.
Thank you.